Hello everyone, I'm Hongyi Lu. I will present not my work titled Notus Dynamic Proofs of Liability from Zero-Knowledge RSA Accumulators. This work is finished by HKUST, that's my school. And I'm presenting on the behalf of Jiajun Xin, who cannot come today sadly due to visa issues. Just as traditional stock exchanges are the backbone of financial markets, cryptocurrency exchanges are foundational to the digital asset economy. Cryptocurrency can be exchanged in two ways, either centralized exchange CEX for short, or decentralized exchange DEX for short. Due to efficiency and customer habits, more than 90% of exchanges are carried by CEX in 2024. However, the security of assets within CEX is questionable and mainly relies on the platform's reputation. Recall the collapse of FTX in 2022. Despite being the third largest CEX globally at the time, FTX collapsed due to inside unauthorized transactions. After FTX's collapse, many major CEX platforms have adopted a proof of sovereignty system. This move aims to demonstrate their financial probity and restore user confidence in CEX platforms. Let's examine the concept of a proof of sovereignty system. A proof of sovereignty proves a CEX platform's asset is no less than its liabilities. Therefore, a CEX platform is only incentivized to prove more assets than it has and less liability than it has. This system contains two components, a proof of asset subsystem and a proof of liability subsystem. We call it POL for short. The proof of asset system aims to prove the platform's ownership of specific accounts containing certain assets. This process is straightforward. The platform generates digital signatures to its accounts, thereby proving ownership of both the accounts and the assets they contain. Conversely, the POL subsystem aims to prove the total funds the platform owns to its customers. This verification must allow any individual customer to act as a third-party auditor. However, the POL system presents significant challenge. Let's see the state-of-art static system model and the industrial practice. The static model has three entities: user, the CEX platform, and an auditor. Users deposit to the platform as the first step. The platform then stores the ledgers to the dictionary, generates a digest for the dictionary, and publishes the digest to a public bulletin board, which can be instantiated by a blockchain. Upon the publication of the digest, each user is required to look up their own liability records with respect to the digest. The platform must reply with valid membership proofs, ensuring each user can verify their own records inclusion. The auditor can audit the ledger for the total liability of the platform. The platform must reply with a proof. For every epoch, the platform proves to the auditor in zero knowledge that all account balances are positive, and the sum of liabilities is correctly calculated. And we need the zero knowledge property because the user's privacy needs to be protected. And we illustrate the example of Binance POL solution. Binance built the dictionary with key value pairs, where the key is the username and the value is the user's liability. Then they further store the key value pairs in a Markov tree and publish the Markov tree root as the digest. Membership proof is the Markov path of each Merkle leaf with log n size and reveals information about neighboring leaves. To prove the well form of the dictionary, Binance utilized SNARK, which is short for Succinct Non-Interactive Arguments of Knowledge. Note that SNARK can prove any relation in NP language with a short proof that needs to be carefully designed for prover efficiency. Binance provides SNARK proof to show the sum of liabilities is the sum of all the leaves in Merkle tree and all leaves are positive. Although this solution works overall, it has limitations. First, accounts need to be proved even if it's not updated. And there is no correlation between each epoch. And there is possibility of privacy leakage and window opportunity attack. I will talk about this attack in the next few slides. In practice, the POL system operates in a dynamic environment. Designing it as a static model leads to several significant challenges. For example, a malicious platform can underreport its liability by either delaying updating users' liability into the dictionary or remove some users' liability temporarily and then add them back when the user queries. The above two attack cannot be detected unless all users check their liability in all epochs. We summarized these attacks called window opportunity attacks. Let's examine this attack vector. In epoch 1, a user, Alice, deposits 1,000 coins to the platform, and the platform's ledger accurately records Alice's liability as 1,000 coins. In epoch 2, Alice becomes inactive. A malicious platform can tamper her liability, reducing it to a lower value, such as 1 coin. In epoch 6, upon detecting signs of Alice's impending returning to the system, the platform can restore Alice's liability to its correct value of 1,000 coin. When Alice comes back to the system in epoch 7, she finds her liability correctly recorded as 1,000 coin, leaving her unaware of any manipulation. This sequence of events creates an attack window spanning from epoch 2 to epoch 6. During this attack window, the platform artificially lowers her total liability by misrepresenting Alice's account. To address this window opportunity attack, we propose a dynamic POL model. The dynamic POL model maintains a structure similar to its static counterparts, with different proofs presented to the auditor. For each epoch, the platform proves to the auditor regarding the updates of that. Firstly, the update is append only. Secondly, the update only appends transaction with a timestamp of the current epoch number. This is to avoid a malicious platform to retroactively inserting fake historical data. Thirdly, the update does not cause any account balance to be negative. And lastly, the sum of all liabilities is correctly updated. In other words, in each epoch, the platform does not generate a new dictionary from scratch. Instead, it updates the dictionary from previous states and proves it's the correct update. To build an efficient dynamic POL system, we mainly rely on 3 tools. The first is RSA Accumulator. It can commit a set to a short digest and provide all one-sided membership proof. The second one is hash chain, which is a classical technique to store a list of changes using hashes. It is similar to a blockchain. In this system, we will input the user ID, its liability, and the update epoch number and previous hash as new hash chain input. The third one is a protocol called MultiSwap, which proves that given a set S, removing a subset Y and inserting a new set X, we get the updated set S prime. Additionally, we can check the relation of set x and set y using SNARK. In this paper, to suit the privacy and efficiency need of the POL system, we extend the RSA accumulate to zero-knowledge RSA accumulators and extend MultiSwap to zero-knowledge MultiSwap. Both of these enhancements have been implemented with minimal overhead, ensuring the system remains efficient and scalable. Due to the limited time, please refer to their paper for technical details. Finally, we present the construction of our dynamic POL system called Notus. In our Notus system, the dictionary is committed using a zero-knowledge RSA accumulator, and the published digest is constant-sized. The membership proof is a zero-knowledge RSA membership proof, which is constant in size. Notus uses the ZK MultiSwap to prove the update is correct for each pair of transactions. That firstly, the deleted old transaction is recorded in the newly inserted transaction hash chain. Secondly, the inserted transaction timestamp is the correct epoch, its current epoch. Thirdly, the updated liability is still positive. And fourthly, the sum of all liabilities is correspondingly updated. There are several advantages of a dynamic POL system. First of all, the prover only needs to prove the updated site, leading to a more efficient prover. Secondly, the transaction history are well recorded in the hash chain digest. User only needs one membership to catch up the whole liability history. Thirdly, the membership pre-computations can be highly parallelized, leading to higher efficiency. And fourthly, the privacy is protected. Let's look at how their Notus system compares against the current industry practice, specifically Binance approach. We built our system using Growth 16 for the SNARK based on GNAC, and we chose Poseidon as our hash function because it is SNARK-friendly and the same as Binance. First, look at the table on the left. We compared three systems. Binance's approach, a bare-bones version we call Merkle insert that captures the basics of Binance's method without their business logic for a fair comparison. And our Notus system, we tested them all with about 1,000 updates. The benchmark result shows that Notus is 4 times faster than updating Merkle trees inside a SNARK. That's a big efficiency gain. Moving to the charts on the right, we are looking at how these systems scale. As we increase the number of updates or swap operations, both the time it takes to generate proofs and the number of constraints in the SNARK grows almost linear to the number of updates. This means our system can handle more users. More practically speaking, Binance have 45 million users in their POL system, according to Binance's own data. Assuming one server with 32 cores, it takes 68 days to generate the proof for all of them. Assuming 100 servers, it takes 16 hours to generate the proof. Because of this inefficiency, Binance is generating their proofs every month for now. Assuming 1 million users conduct transactions within one epoch, with 32 such servers, Notus takes about 47 minutes to prove the correct updates of the POL for one epoch. In summary, in this work, we first identified the window opportunity attack of static POL model and propose our dynamic POL model. We provide new tools based on RSA accumulators with many optimization and provides first construction of a dynamic POL system. Our experimental code is available in this GitHub repository. And thanks for listening. Sorry I cannot take any questions as I know little about crypto. So please send the email to the original author. Yeah, thank you very much. Yeah.